Okay, so today I'm going to be talking about nuclear fusion, a pathway to the future. So, nuclear fusion has been around pretty much forever. It's the force that or the way that our stars are powered in space, and it pretty much gives a lot of pretty much all life is has energy from nuclear fusion. So my key points today, I'll talk about what is nuclear fusion, how does nuclear fusion work, is nuclear fusion in the future, and what could this mean for society? Okay, first thing, like I said, each star in our universe receives energy from nuclear fusion. That includes our sun, everything. And scientists are now working to recreate this process here on Earth so that we can get our energy the same way that stars get their energy. So, how nuclear fusion works. Nuclear fusion is the thermonuclear reaction that combines hydrogen isotopes into helium. And there are two primary fuels used for nuclear fusion, deuterium and tritium. Both are isotopes of hydrogen and are both heavier than average hydrogen. Deuterium is the heavy isotope of hydrogen, as I stated, and it contains an extra neutron than protium. So that means it has one proton, neutron, and electron. So, yep, just like I said there, its isotope name is hydrogen 2, or H2 pretty much. And where is deuterium found? Well, this is I found this very surprising. I'm sure you will. Ocean water is the primary source of deuterium. So we could be powering ourselves using an isotope from ocean water, which is a crazy thought to think of. And now the other fuel is tritium, which is the heavy isotope of hydrogen. And this one contains two neutrons, one proton, and one electron. So this one's heavier than, like I said, H3 here. But of course, there's an issue with this one. And the issue is tritium is one of the rarest substances on Earth. There's not much of it around. So, which is really surprising because I found that only 7.3 to 20 kilograms even exist on Earth. Which, if you think about that, it's crazy because that's probably like, I don't know what I weigh in kilo. Oh, I guess I do. It's about, less than half of my weight. Which is just crazy to think about. And another issue is most of it's already being used in nuclear warheads, which I don't think they're giving those up anytime soon. But there's good news, though. There may be a solution to this. Well, could be debated, but most scientists believe that helium-3 could be used as a substitute for tritium. Helium-3 is an isotope of helium, and its structure enables it to, as it has two protons and one neutron, and still needs the neutron. So this allows for fusion to occur, but it's slightly different and yields different products. Actually, the use of helium-3 they found is actually more powerful than regular tritium in their reactors. Or it would be in an equation anyway. But here's another issue. Helium-3 isn't that plentiful on Earth. However, it's plentiful elsewhere. Well, the moon. The moon actually has quite a supply of helium-3 because of solar winds coming from the sun. Well, that becomes complicated now because to get the helium-3 we need to operate our reactor, or the large amount, we'd have to create a moon base or start moon mining to get some of that helium-3, which just furthers the argument why we should be working to get to the moon. Okay, so now the reaction. So the stars that we know perform this are under massive pressure, which transitively makes them very hot. How hot? It's approximately 15 million degrees Celsius in the sun, which is 681,818 times more warm than this room is right now, which is just crazy to think about. And at these temperatures, the atom structures dissolve and the electrons are released from the nucleus. So the nucleus stays together, but the electrons just leave. And this creates a state called plasma. So plasma, as you can see here, this is a state of matter that consists of an ionized gas, and the electrons are stripped away from the gases and are just free-flowing along with the nuclei. So plasma nuclear fusion must sustain its temperature to continue the reaction, which is one of the issues with trying to create nuclear fusion, is the sustaining that hot of a temperature for that long of a time. Because a lot of the reactors that they've had have gotten very hot. Because I was reading about one in China that they were able to get run for about 2 or 3 minutes before it got too hot and overheated. So what happens in the plasma? So due to the extreme pressure and heat, the deuterium and tritium nuclei start moving around very violently, and the nuclei are all charged positively as we have lost the electrons from them. So electrostatic forces normally repel these. However, the speed at which the nuclei are traveling overcome these forces and result in fusion. So here's some diagrams here. Yep, these are the forces between these atoms. They want to push away, but the forces, they have enough force to overcome that. And over here, this is the model of the reaction here. So the deuterium and the tritium react. Helium-4 is produced, which is stable, and then about a neutron is released with 14.1 mega electron volts are released. So nuclear fusion energy. So scientists have been working on creating nuclear fusion here on Earth. So there are a lot of benefits. Before you say, oh, it's nuclear energy, it's probably terrible. We're going to have a bunch of barrels of radioactive waste sitting in a bunker for thousands of years. Well, hear me out. Benefits. So the benefits of nuclear fusion is there's a large amount of power generated, which is very good because ITER, which we'll be talking about a little bit later, is the International Thermo something reactor. I can't think of what the E stands for. Could be capable of producing 500 megawatts of electricity, which is a lot. There are very little environmental impacts by the operations of these. The only severe risk that they have is tritium leaks, because tritium is extremely radioactive. But still, there would be such a small amount of tritium in the reactor itself that it would not even be extremely dangerous. And it would likely be, it'd likely mix with the oxygen and turn into radioactive water, but there'd be such a small amount of it, it would be either diluted or would have minimal impact on the environment. And another thing is that there would be no CO2 emissions, which is something that one of the number one benefits of why we should be researching fusion is that could be a major contributing source to solving the issue with global warming and climate change. Okay, so now I'm going to explain fission versus fusion. They're kind of different. So fission is where you split heavy metals like uranium or plutonium, and you split them off, and there's energy made. But with fusion, you're putting atoms together. So they're kind of the same thing, but they're very different. So they produce. So I can't really say if a fusion reactor would produce that amount, but they're predicted to. So that's why I put that little asterisk there. They produce nearly the same amount of energy as a nuclear reactor, as a fission reactor, which is about 500 megawatts. Fission produces radioactive waste that takes thousands of years to decay. Now, fusion does make nuclear waste, don't get me wrong, but it takes a lot less time for it to become non-radioactive and decay. So fusion can also result in fission can result in dangerous reactor core meltdowns that release large amounts of radiation, like your Chernobyls, that one in Japan, 3 Mile Island. Those were all bad core meltdowns on fission reactors, and those can harm the environment. They cause cancer. It's not good. But fusion reactors, if they get too hot, they'll just be turned off and they'll cool down, which is the great part is there's no risk of a major meltdown being ran there where large amounts of radiation are released. So here is a chart with some of the different types of designs that are being made right now. The most promising is the tokamak, which is pretty much a donut-shaped reactor. All the other ones really, they've tested them. These are a little bit later from like the 90s, and this one didn't come up as much, but this one was a reactor from, which is really neat. I'm going to talk about this one briefly because I thought it was really neat. At this laboratory, I can't remember the name, but it's an American laboratory. They have a pellet of fuel, densely packed fuel, and then they shoot it with some of the world's most powerful lasers, and then that produces the heat to create the fusion energy. But this one here, the tokamak, is what we're looking at as most likely being the working model, which is your ITER, which we'll get to here in a second. So ITER, I've been talking about it. Let's talk about it now. So it's the International Thermonuclear Experimental Reactor. This is located in France. It's a project between the ES, European Union, China, Korea, Japan, and Russia. And it's very expensive. It's about $5 billion. And it's the largest, most promising reactor project yet. Because we've had previous experiments with different reactors in different countries. And this is kind of the combination of all the knowledge that we've gained from them. So I found a lot of very interesting statistics about ITER and just the sheer size of what they're doing, because it is honestly gargantuan in size. So they used 100,000 kilometers of niobium tin wiring, which is approximately 62,137 miles, which is, I believe that's about a couple times around the center of the or maybe around 2.5 times around the Earth's equator. And that is just crazy to think about. It will sustain a temperature of 150 million degrees Celsius when it's running, which is about 10 times the heat of the sun. The tokamak will weigh nearly 23,000 tons, which is about 25,352 tons, which is just mind-blowing. And the total facility weight will be about 400,000 metric tons. So the central electromagnet inside, I talked about how it's like donut shaped. So the thing in the middle will feel sustained force equivalent to twice the thrust of a space shuttle launch, which is about 60 meganewtons of force. And the main chamber area will stand about 200 feet tall. So why is this such a big deal? ITER promises they can do what's never been done before, which is will hit a Q value of over 10. Now, you might be wondering what Q is. Q is the ratio of energy produced to energy required to sustain the reaction. So in fusion reactors, it takes a lot of energy to start the reaction and keep it sustained. But we haven't gotten to the point yet where we're actually gaining energy out of it. We're just putting more energy in, and it's not generating the same amount of energy that we're putting in. So we're losing energy pretty much when we operate them. The closest one it's gotten so far was JET, an American reactor, same model in the 90s, hit a Q of about 2/3, which isn't quite close to 1 yet. So this means that it'll produce 500. So if it produces 500 megawatts of electricity, it'll take 50 megawatts to operate. And this could also drive a new commercial sector of nuclear fusion reacting companies that are interested in this to make money, which would be very big. Now here's some pictures. So you can see here, this is one of the designs for ITER. So on this side, you can see how it's all lined in magnets, and that's part of how they get the pressure to get those reactors to work. And here you can see, so they kind of, darken this side just to show you. This is kind of what it looked like with the plasma running through there, which is really interesting looking. This is a construction project from, I believe, a couple years ago. I'm going to go back. there from a couple years ago, and you can see that it's just really large in scale and size. So what impact could this have? I'm going to focus particularly on this. So United States greenhouse gas emissions in 2018 was 27% for electrical generation, which is primarily from coal, natural gas, oil burning to get fuel. Well, this could have a tremendous impact on the electrical scene in the United States once one is functioning, because this could cut greenhouse gas emissions with mass implementation. This is because right now we are able to use renewable energy sources, but they're just too expensive to massively implement without incurring high energy bills and possible economic damage. So this won't make electricity, this won't affect the electricity, but it'll affect all of this, because once we get more electricity that's clean, more cleanly generated, you will probably see transportation shift also to more electric vehicles as well, which will affect your transportation emissions as well, because your electric vehicles will be powered by cleaner energy than if you're plugging your car in next to a coal power plant. It's most likely a coal-powered electric vehicle. So that is. So I'm also going to talk about how other things that we could be doing with our nuclear fusion, because it's not just electricity, but we could be also using this for long-term space travel as well, because there's also been, physicists have been thinking about how it could be applied to space travel, and it could be powering our space vehicles, which would make them through deeper space when they're moving fast, because they can move up to 3 times faster than your average space vehicle. If, at least theoretically, it'd move about 3 times faster, which would make it much faster to go see other parts of the solar system and galaxy. So I'm going to talk briefly about what I think we need to be doing with these electricities. So what we need to be doing with nuclear fusion as far as fuel, I believe we need to be decommissioning our coal, natural gas, oil, and nuclear fission in the long term. I think that we need to throw taxes on CO2 fossil fuels and coal fire plants, and use that money to invest in research and additional tax breaks upon renewable energy companies, and also invest in the research of nuclear fusion more than we are right now. And this would expedite the fusion research, because when I talked to one of the doctorates in nuclear engineering from SDSU, he said that it's all about how much money you put into the program. If you're going to put a whole ton of money in, you're going to get results a lot faster than if you put, as much as we are in right now, because it's the time frame of when this could be developed mainly focuses on how much money we're putting in, because most sources say that we could see it in 2060 to 2070, but some say that we could be seeing nuclear fusion power as soon as 2040 become on the mainstream scene. But it all really depends, because ITER is going to be functioning in 2025 with experimental, and then they'll try and sustain it by 2035. So, and then we also need mass implementation of these fusion technologies once we have them available and we've tested them. And then after that, I believe we need to continue growing our renewables and then decommissioning all of our unrenewable power plants. And so that has been my presentation on nuclear fusion.
3, 2, 1.
I'm out of breath now.
You guys can ask questions. I'm going to stop this. Please be quick on the questions. We're going to run out of time for everybody.
Yeah, that's a new one. Marley.
So you said that nuclear fusion
you stopped your recording.
less chemical waste than fission, right?
Yes.
So you said that in order to